Hello, so let's learn about Joan planets, the gassy planets. That include Jupiter, Saturn, Uranus, and Neptune. So let's look at all these planets in short. So the term Joan is derived from Jupiter, the largest of the outer planet and the first to be observed using a telescope by Galileo in 1610. So taking its name from the Roman king of God, Jupiter or Jove, the objective Joan has come to mean anything associated with Jupiter, and by extension, Jupiter-like planets. So all these four planets are called the Joan planets because it's most likely Jupiter. Anyway, so after the asteroid belt, we can find the Jupiter in the solar system. So distance from the sun is about 5.2 astronomical unit and mass is 318 times mass of Earth. And the density is 1.33 grams per cubic centimeter. So you see like the density is very small compared to the terrestrial planet's density. The composition is mostly hydrogen and helium. Now, so the Jupiter is 11 times the size of Earth. And let's move on to the Saturn. So the distance to Saturn is 9.54 astronomical units, and mass is 95 times mass of Earth, and the density is 0.71 gram per cubic centimeter. And the composition is mostly hydrogen and helium again. So as you see, all four planets composition is mainly hydrogen and helium. So Uranus, the composition is hydrogen compounds, a little bit of rock and hydrogen and helium. Then again on Neptune, the hydrogen compounds, rock and hydrogen and helium. So the density is 1.24 grams per cubic centimeter on Uranus, and for Neptune, the density is 1.67 grams per cubic centimeter. Then the mass of Uranus is 14 times the mass of Earth. Neptune's mass is 17 times mass of Earth. And the distance from the Sun to Uranus is 19.2 astronomical unit. Then to the Neptune is 30 astronomical unit. That's the size comparison with the Earth. So it's not about like how many Earth can fill in there, but it's about like how many Earth can you fit across the diameter. So you can fit 11 Earths across this one, and here 10 Earths. Then the Earth, the Uranus and Neptune about 4 times the size of Earth. Rotational period is 9 hours and 56 minutes for Jupiter. Saturn will take 10 hours and 42 minutes. Uranus, 17 hours and 12 minutes. Neptune, 16 hours and 6 minutes. All right, so the formation of Joan planets. So far from the sun in coldest region of space, icy planetesimals survived. So for very large Joan planets formed at least 15 times Earth mass. So they are comparatively very large. Then once the planet has grown to such a large mass, it has a strong gravitational acceleration or the gravitational pull, so it can capture gas directly from the solar nebulas. So we'll learn about solar nebulas after we're done talking about the Joan planets. Then the solar nebula is 74% hydrogen and 24% helium and 2% of heavier elements. So there's no wonder why we think that these big giant planets grab hydrogen and helium from solar nebula, right? So we have mostly hydrogen and helium gases on Joan planets. Then the Joan worlds are very low density worlds but they are rich in hydrogen and helium. And also, all these 4 planets does have disks or the rings around it, even though Saturn is the famous planet to have its own colorful rings, but all these 4 planets does have disks of their own. And on those on those rings, we can find moons that's condensed. So when we're talking about Jupiter, the great red spot is a very famous scenario happens on on Jupiter. So as you see here, this is the red spot. So in these pictures, you can see it's kind of a storm, right? So it's creating its storm and is changing its size and the speed, maybe like from these pictures. That's what we can see. So let's look at in detail about this scenario. So the surface consists of clouds of ammonia, hydrogen sulfide, and water. The bands are circulating in opposite direction, causing turbulent vortices to form between them. So that's create a what we call the great red spot. So it's kind of a storm on Jupiter. So this circular storm is about 40,000 kilometers across in the southern hemisphere of Jupiter. So as you see here on this animation, let me go back. So you see like it's circulating, right? So this is the great red spot. So as you see, all these air or the gases are moving really fast, making that storm, which is 40,000 kilometers across. As I mentioned, Jupiter is 11 times the size of Earth, and it's thought to be large as a planet can get. This is the largest planet in our solar system. So in this picture, you can see comparative size of Earth and the Jupiter. So adding more materials to it would cause it to become more compressed so that it would sink. So if it drag more materials, then it's get more dense and it can shrink to a small size object. So the Jupiter's oblate, it's flattened at the poles due to its rapid rotation. Its equilateral diameter is 6.5% greater than its polar diameter. So it's not a perfect circle. It's kind of an elliptical shaped object. It's oblated. A star such as our own sun can be much larger because it has nuclear reaction generating energy at its center. So if you think about the sun, it is really big in size. So it didn't shrink, as I mentioned earlier, because it does have a nuclear reaction going in there. So it's producing its own energy to keep that going. But Jupiter is different. It's a planet. It's not creating its own energy. So if it's grab more particles or more getting more heavier, then it's can be shrink. The intensity of sunlight at Jupiter is about 1/25th of its intensity at Earth. The surface temperature is negative 234 Fahrenheit, so it's really cold. Jupiter still retains heat at its center, and its surface receives about as much heat from its interior as it does from the sun. So if you remember, on Earth, there are sources of energy. One source is coming from the center of the Earth, right? From the hot magma inside. So on Jupiter also, there's a hot center, so it can provide some energy onto the surface. Then the orbit and rotation period, as I mentioned earlier, Jupiter rotates on its axis once in slightly less than 10 hours. And its rotation axis is tilted very slightly, which is 3.13 degrees from the perpendicular to the plane of its orbit. And the Jupiter's orbit around the sun is very much elliptical. So the perihelion is 4.95 astronomical unit and aphelion is 5.45 astronomical. It takes about 11.86 years to go once around the sun. So year, right? So 1 year on Jupiter is 11.86 Earth years. Jupiter is oblate. as I mentioned earlier, due to its rapid rotation. So equilateral diameter is about 6.5% greater than its polar diameter. Interior of Jupiter, so it does have a liquid metallic hydrogen inside and molecular hydrogen around that. So this little dark blue color ring is the liquid metallic hydrogen, and then around that we have it has molecular hydrogen. So as you see, there's a liquid metallic hydrogen that tells you something about Jupiter's magnetic field. And look at the size. So size-wise, it does have a big region, higher region of liquid metallic hydrogen. So that will produce a magnetic field on Jupiter. So there's a good magnetic field on Jupiter, which is about 10 times the intensity of the Earth field. Over a much larger region of space. So you can imagine, like, it's relatively big in size compared to the Earth, and that's create a bigger amount of magnetic field as well. So it does have a very strong magnetic field around it. So the currently accepted model of how planets generate magnetic field is from the rotating liquid metallic core. So this planet, Jupiter, does have a metallic hydrogen liquid in there. Then the Jupiter is certainly rotating fast enough. As I mentioned earlier, it's moving really fast, but it does not have a iron core in there. So there's no metallic iron core, that solid iron core in there. It is thought that the extreme pressure at the center of the planet causes hydrogen to become liquid metal. So this is the rotational axis and the magnetic axis of the Earth and Jupiter comparison. So as you know, our magnetic axis is 23.5 tilted from the rotation axis. Now here there's a 10-degree shift between the rotation axis and the magnetic axis. So Jupiter, as is the case for Earth, the magnetic north and south poles are displaced from the poles defined by the planet's rotational axis. That causes the magnetic poles to be carried with the planet's rotation and provide a reliable way to measure the rotation of this non-solid planet. Although the poles are displaced, a line drawn between them does go approximately through the center of the planet. So this is what I mentioned. So here, that's the rotational axis and that's the magnetic axis. They all cross at the center. Right? Even on Earth, the rotational axis and magnetic axis crosses at the center here. But there are other planets which doesn't show this quality. All right, so please answer the question on top pad.